In this part, we shall present feed-forward disturbance compensation. Before, we already developed PID controller for disturbance rejection mode. This is namely the disturbance, and the disturbance influences through this path to the controlled variable. And of course, this information comes to the main controller, and this controller reacts on the way to compensate through this path, this disturbance as much as possible. But due to time constants, due to big delay, mainly in the process transfer functions, this reaction is rather slow. In this experiment, we do not use the auxiliary controller, which is intended for the later cascade control. So this auxiliary loop is set to 0, and this auxiliary gain of the controller KPP equals 1. So these are the basic parameters. The reference is 0, so the reference signal is 0. The disturbance is 0.5. This is the disturbance. And then we use KPZ. This is the gain for the feed-forward compensation. We use the value 2, and we use the optimized values of the PID controller. Let's remember this table. This table was obtained by optimization, and this second row is intended for the disturbance rejection mode. So we can find these three parameters for PI and D part of the controller, and we also notice that the starting value of the criterion function was 104, and after optimization it was much smaller, about 13. So these are the parameters of the optimized PID controller. And why we use this gain of the feed-forward compensation? Namely, the feed-forward compensation goes through this path. There is one assumption that the disturbance can be measured. We measure it, we lead it into a proportional gain. This is then so-called proportional disturbance compensation, and we act with this signal to the control variable very fast. And why do we select this gain 2? The disturbance equals 0.5. This is gained by 2. That means in this place we obtain the signal 1, and at the time 0, another input of this summer is 0, because the reference is 0, and we obtained here the signal 1. It is multiplied by KPP, which was 1. We obtained here the signal 1. This is multiplied by 0.5, and we obtain here 0.5. But also because we have a minus sign here, this is actually minus 0.5. So this signal completely compensates the disturbance signal at time 0. The situation is just the same in the steady state, but of course we cannot achieve that the compensation would be perfect in the Holt transient response. Now I will select this part of the program. I press F9, and I obtain two windows with results. In this window, there is the output of the process. This means this part, this is the controlled variable or the level in the third tank, and with the green color we obtained the single loop situation, single loop control, and with the blue curve we obtained the results with feed-forward compensation. And of course, we can observe that the behavior is much better. What we would like to achieve. In this case, the reference signal is 0. So this is also the desired value for the control variable. And of course, the disturbance should influence to this control variable to the level in the stir tank as small as possible. We can see that the influence of the disturbance in the case when we use feed-forward compensation is much smaller. One important thing is that these peaks are much smaller, but it is also important that this response has as much as possible the symmetric behavior. So we have here a positive peak, a negative peak. These are much more similar than in the case of green curve. What are the peak values? The green curve has the peak value 0.09 approximately, and the blue curve has the peak value 0.05 approximately. This means much less. Another window shows the responses of the control variable. This is this signal at this place in the scheme. Again, the green curve is for the single loop and the blue for the feed-forward compensation. Both responses are rather similar, but the big difference happens in this initial part. What we can observe in this initial part, we can observe that the starting value in the case of single loop control is 0, but in the case of feed-forward compensation, the starting value is -1. And this value is just the same as the value in the steady state. So with this effect, we improved significantly the elimination of the disturbance.